Okay, let's get started. So my name is Abu. I've been the cameraman for this course for, as you probably noticed. And I'm going to give you the review session for the midterm, which we're having on the 15th, which is on Wednesday in class. And here I've just listed the basic topics that we may ask about in the midterm. And so I guess I'll just go over them. Can everyone see this okay? Maybe I should raise it up. Yeah. Hi. Say again? The microphone?
Yes, can you raise the volume or something?
I'm not using a mic. I'll speak louder.
Okay.
But can you guys see this? Or should I lift it up? Let me raise it up. Okay, so we're going to basically cover things, the classification unit that we've presented in lecture. So this includes the basic the linear classifiers, logistic regression, the perceptron, naive Bayes, and SVM. And for the perceptron and SVM, we want you guys to understand how to kernelize those methods because they're very common applications of kernel methods. So we also want you to know the distinction between generative and discriminative classification and be able to explain what makes a particular approach generative or discriminative. We also want to cover basics. This may be tested through other questions, like asking about some of the other topics. But these basics include basic linear algebra, vector calculus, know how to work with matrices and vectors, know how to take derivatives with respect to vectors, and some basic probability theory. So this includes things like understand what independence is, conditional probability, conditional independence, Bayes rule, product rule, so things like that. And we also want you to understand how to estimate parameters by maximizing some likelihood or posterior. This is MLE, MAP. So if you understand both those methods, that would be good. And then more recently, we also covered linear regression and kernel methods. We want you to understand linear regression pretty well. You don't have to understand anything beyond linear regression. So that includes polynomial regression, Gaussian processes, kernel regression, just linear regression. Then we also want you to know what regularization means and how it's related to priors and what it does for what it gives you in various machine learning algorithms. And finally, we also want you to know, we covered this in lecture, the trade-off between bias and variance in machine learning algorithms, and how the complexity of your model affects both of them, and how much training data also affects both of them. So that's basically just the list of topics, and now I'm just going to, I guess, open the floor to questions. I can go into detail about any one of these topics. Does anyone have a particular one they want me to go to first?
Can you go over
SVMs? Sure. So let's see. Okay, so the basic idea behind SVMs is that you want to find a linear separator between your data points, right? So so what is the best linear separator in some sense? Someone want to answer that question? Yeah, so the linear separator that gives you the largest margin, some would call that the best linear separator, and you want to find that. So let's see. So suppose you have some data points. There are lots. This is linearly separable, so there are lots of different possible separators, linear separators that can perfectly discriminate these two data sets, right? But the one that you want to find in SVM is the one that maximizes the margin, which is the distance, the largest distance from a training point to the separator. So in this case, the margin would look like this, or the separator would look like this. I can't draw. And you're trying to maximize this distance, which is your margin. Yeah, so let's see. So you can write that as an optimization problem, and it's a pretty easy one. It's just So we showed that 1 over the norm of W is one way you can express your margin. So minimizing that is the same thing as maximizing your margin. And then you want to make that subject to the constraint that all your data samples are correctly classified, right? So that's what that means. And so this is the hard margin SVM. Where we don't allow any mistakes, margin errors. What you can do is you can somewhat relax this condition. And here h is some sort of loss function for misclassifying a point. The 0, 1 loss, you could use that where if you misclassify a point, it gives you a penalty of 1. Otherwise, it gives you a penalty of 0. But that is very difficult to optimize for. In fact, it's NP hard. So instead, what we do is we use a hinge loss function, which is an upper bound of the 0 loss function, and it makes the problem convex. And so it gives us nice properties that makes this problem easier to solve. Yeah.
So do we pay a cost for both margin errors and for misclassifications? Are they both described by C times H?
Margin errors and misclassifications. Yes, C is like a trade-off parameter that basically says how much do I want to maximize the margin versus how much do I want to reduce margin errors. And so if you can prioritize one over the other more heavily by changing the value of C. Yep.
So why is it that only the support vectors determine what the decision is? Is that true?
Yes, yes, that's true. I mean, if you were to look at this data set, I mean, intuitively, you can remove this point, right? And the support vector wouldn't change. The only point of area of interest in this space is, the place that's close to where the classes change. So it makes sense that if I add lots of minuses here, that the support vector shouldn't, the linear classifier shouldn't change, right?
Because the minimization problem didn't change, right?
Yeah. Yeah. In fact, in the dual form, you'll see that the non-support vectors are assigned weights of 0. Right? Basically, they have no influence on the decision boundary. Yep.
Could you please explain why, when there's an intercept term, then the lines in the middle, and what happens if there's no intercept?
Sure. This was a common, I guess, misunderstanding. we can add an intercept term just by adding a dimension and setting those values in that dimension to 1. So suppose I have a vector x, right, and I dot product with a weight w. And you're saying that how is this different between some intercept term, w0, right? I can easily just make this, just add a dimension to x. So suppose I make this x prime, which is just, the vector x plus a 1 at the very end, right? This dot product will give me this thing, effectively. So that's an easy way to add an intercept term to many of our linear classifiers we found.
So my question is, why can you add the intercept term that lies in the middle of the two margins in the middle, and what happens if there's no intercept?
Say the first part again? I didn't catch that.
So if there's intercept term, right, in the set vectors in the right middle of the two margin lines.
Yes.
Why is that? And what happens if there's no intercept term?
Well, that'll depend on where the origin is, right, in this space. For example, if there's no intercept term, then I can only get this particular linear classifier if the origin is somewhere on the classifier itself, right? But if I allow an intercept, for example, by doing this, adding a 1 to all the x's, then the origin doesn't have to be anywhere. And this will find this particular classifier every single time, right? So if your data, for example, is linearly separable with respect to the origin, like a separator has to go through the origin, then you don't have to add an intercept term. And you'll find a good linear separator. But if it's not, then you should consider adding an intercept term or doing the soft margin.
So if you just draw, what if there's no intercept term? Can you just draw a possible separator?
Where do you want the origin to be? Where do you want the origin? So for example, if these are your axes, this will be the exact same because it goes through the origin, right? But if, for example, if that's your axes, then hard SVM won't give you a separator. It'll fail. Does that make sense? Yep.
Can you explain what the normal W is doing?
Normal W is a margin. Let's see. Okay. Do you know the answer to this question off the top of your head?
Sorry, I just got here. What was the question?
Why is the norm of W in a linear separator at the margin? One over the norm of W is a margin. Yeah.
It's fine.
Yeah. Yeah, I have to go through the math in my head. Anyway, I'll look that up more carefully offline because I don't know the answer off the top of my head. I have to go through the math. But yeah, that's a good question. Anyone else have any other questions? Yep. Say again? I didn't hear you. The answer to Piazza? Okay, yeah, sure. I can do that.
What is the Bias-variance trade-off?
Oh, yeah. Let's see. So suppose you're doing regression, right? And I want to fit these data points. Actually, let me make these. And I want to try a polynomial regression, right? Just as an example. And a polynomial order 1 will fit this like this, right? Polynomial of order, let's say, 3 may do something like this. And I can keep increasing the order. Eventually, I'll get a polynomial of order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, which will do something like right? So the polynomial of order 10 fits these points exactly. It's perfect, right? So the bias in that case is 0, right? That's the error on your training data. However, the variance for a polynomial of order 10 is very high, because suppose I get another point like this. That's going to be pretty far off from this, high up peak in this very wiggly function. So you can kind of see that as I increase the complexity of my model, in this case the degree of the polynomial, the bias goes down, but the variance increases. Right? So if you plot bias and variance with respect to complexity, let's see right here. Bias will look something like this. Whereas variance will look something like this. And your expected test error is going to look something like this. Right? So I guess one way to pick the correct degree is to find this point. Right? So the key is that the bias and variance they go against each other, right? As you increase the complexity, your bias decreases, whereas your variance increases. Yeah.
What's the definition of variance?
Definition of variance. So intuitively, the variance is just how well does your model perform with new data on expectation. There's a mathematical definition that you can see in the slides from nonlinear regression that Artie posted. I don't think it's useful to put them up here because they're a bit involved and they're somewhat specific to regression. But in general, it's how well your model performs for new data. Suppose I give you a completely different training data set, asked you to find a curve that fit it, right? does that curve change a lot is basically what variance captures. Yep. Yeah, sure. Let me get the exact. Yeah, so suppose I give you a set of training data, right? And I ask you to fit that training data to the model, right? So that you have, like a polynomial regression, for example. And then I give you a completely different training data set, right? That I picked randomly. And then I ask you to do the same thing again. And variance is basically how much your fit changes, varies over random samples of training data. So if I have a polynomial with degree 10, then it'll be very sensitive to where the points are, right? The function is going to wiggle in very different ways. Whereas a polynomial degree 1, a line, won't be as sensitive to different training data sets. Yeah?
Is this training, each training random training set?
Yes.
Is different, so they don't have the same examples in them?
Yeah, exactly. Exactly.
So they're kind of new. So we can think about them as a test set.
Say again?
So we can think about them as a test.
Yeah, in a sense, you assume that they're drawn from some hidden distribution of examples, and your test examples are also drawn from that distribution.
So why isn't it the best case when my variance is low? Because you wrote up lines with test errors.
Yep.
And you wrote up the variance. And there's a point when your variance is very low. So it seems like it's good because you're performing well all test sets, but your test error is still high.
It's because the bias is is another factor to what determines your error, your test error. The bias is like how well does your model fit your data, the training data set that you have right now, right? So a polynomial degree 10 can just go through every single point and you'll have a bias of 0, right?
Oh yeah, so the variance is not how performance compared to each other, right?
Say again?
Variance is just for each training set, how they
Yes.
compared to each other.
Yes, that's right. Yep.
So, did you get something with functional analysis in the test? Like all the stuff that was taught after the kernel was like the functional space?
Oh, like RKHS stuff? I would say you should know about them because we spend a lot of time in lecture. Maybe like what makes a kernel a good kernel, right? Like if a kernel doesn't intuitively measure distance in some way or closeness in some way, that's not a good kernel, right? So things like that. If you understand like the intuitive interpretation of what makes a good kernel, then I think that's fine. I don't expect you to know like the mathematical details and like the theorem that says that, you know, for a given kernel, there's some sort of feature map which maps to some infinite dimensional space or high dimensional space, right? Yeah, so. Any questions? Yep.
Can you explain the regularization?
Regularization?
Yes.
Okay. So, let's say we have a model and we want to use MLE to find the parameters, the hidden parameters, and learn that from the data, right? So you have some likelihood. So let's say this is your objective. I don't know, mu. You have some log likelihood, let's say, and you want to find the value of mu that maximizes it. Sometimes that works very well. But for example, if you have a lot more dimensions than you have data points, like let's say you have 10,000 dimensions, but you only have like a couple hundred examples, then it may easily overfit, and you may have problems learning it to begin with, depending on what the exact form of your likelihood is. So one thing you can do is to use regularization, where you just add a term here. So here I'm just computing the L2 norm of the parameter mu here, and that's the L2 regularization. You can also do the same thing, instead using L2 norm, just L1 norm, which is the absolute value, and that'll give you L1 regularization. And the reason why they're connected to priors is because if you have some sort of model for which this is the likelihood function, then the L2 norm corresponds to the case where your hidden parameter mu is drawn from is normally distributed with 0 mean. I don't remember if this is the exact variance term, but the math comes out so that a lambda comes out here. And similarly, if you have L1 regularization, you assume that the hidden parameters, it's identical to as if you put a prior on the hidden parameter that is Laplace distributed. Yep.
So as a and this is all the regularization, we put I put storing on the value of the value of the parameters. So why that parameters why if we put it that way, then this will have to make have a better performance.
Well, it depends on the situation, right? Like in certain cases, L1 regularization, for example, the Laplace distribution looks something like that. It has a kink at 0. And so because it's so pointy at 0, it kind of tends to pull weights closer to 0 itself. And so if you're looking for maybe like a sparse weight, like you want some of your features, the weights in your hidden parameter to be 0, then L1 regularization is one way to do that. But in some cases, you don't want to use regularization. It depends really on the scenario, on the situation. But if you have lots of dimensions compared to data points, you tend to want to use some sort of regularization, because in that case, the likelihood is kind of like your the contribution from the data, but you don't really have that much data compared to the number of dimensions. So you kind of want something else to help you smooth out, right? Any other questions? Yep.
If there is a function mapping from the example space to the Rn space, and then the inner product of the function will be a kernel. I don't know why. It is a question in the online question. What's the necessary property for a function to be a kernel?
Say the first part of your question again. Didn't get that.
If there is a function mapping from the example space to the Rn space, and then applying the function to the two training data, and then do the inner product of the result, then it is a kernel. Okay?
Yes.
Yeah, I don't know why. Why it is a kernel?
So you're saying, let me just make sure I understand. So you're saying you have some feature map, right? Goes from, which is like phi of x, and phi goes from some sort of example space, you know, Rn, to some higher dimensional, potentially infinite dimensional space, right? And you're saying that you don't understand why you can make a kernel just by taking the inner product of applying the feature map to 2 points. So you can kind of think of do you understand the notion of positive definiteness of a matrix generally?
Yes.
Okay, so you can kind of think of a good kernel is like positive definite. It's like a matrix that's positive definite, right? And positive definite matrices can be, suppose I have a positive definite matrix K, right? I can take any positive definite matrix and I can decompose it into a vector. Well, it's a grand matrix of a vector, so. transpose. Roughly. So this is basically saying that like a good kernel is one that is positive definite in a sense. And what that means physically is that it provides a very good measure of distance, between points. Points that are close together will have a certain, a certain value of the kernel, whereas points that are further away will have a different value. And I can construct any kernel just from using these kind of feature maps. If I have a list of points, I can take a feature map and compute the inner product between every single pair of points, and that'll give me a kernel.
So if a function is positive definite, then it is a kernel. Right?
I think that's all the properties. Let me check. Yeah, if the function has to be positive definite and symmetric, yeah. Oh, yeah, this is not exactly the notation. Let me find. Yeah, so for any positive definite matrix K, I can find some points, x1 through xn, such that Kij is equal to the inner product between xi and xj. So that's kind of analogous to this. A kernel is almost like a positive definite function, if you will. Yep.
Beginning of the class, did I mishear you said we maybe use kernels in logistic regression? Or did I mishear that? Or did I say that?
Logistic regression?
Like any entire mapping in logistic regression, but is that like something that would be tested on you?
Oh, I guess I don't think we mentioned that specifically, but that you can do that. I'm not sure if that can be kernelized in the sense that you may not be able to implicitly represent the higher dimensional space using your lower dimensional space. Yeah. Okay, yeah, it's not logistic regression. Oh yeah, sure. So a positive definite matrix is a matrix that has a lot of ways to characterize it. The easiest way in my mind is that all of its eigenvalues are positive. So it kind of is like a generalization of a positive number in matrices, in a sense. Yeah, I think the key is that for the formal definition, I think, is for any vector v, if I take v transpose times the matrix times v again, that'll give me a positive number. So in a sense, this is like saying distances must be positive, right? I can find the distance between two vectors v with respect to some matrix k, and I have the constraint that it must be positive. So that's something you want from distances, right? You don't want to have negative distances. Yep.
I don't imply that we will be able to distance measure the kernel will be able to distance
Hey, can you guys keep it down? I can't hear this question.
I can hear you. Could you say that from the beginning?
Yeah, so you said it means if it's a positive semi-definite, then it will be a good distance measure.
Positive definite. Yeah.
But then applies it.
Because then you don't get negative values from this computation, v transpose kv.
Oh yeah, you know.
Yeah, you don't want negative distances. Yeah. MAP? Sure. So let's say I have some model that where I have points xi, right? And they have class labels yi, either +1 or -1. I'm doing classification, let's say. And I have some sort of prior, for example, the prior on the class assignments will be, I don't know, p, okay? So like, for example, every point has a 30% chance of being labeled +1, and there are 70% chance of being labeled -1. That's my prior belief, right? Spam or not spam was the example we used in class. Then MAP is basically finding the value that maximizes the posterior. So let's see. Yeah. So suppose I want to learn p, right, which is your hidden value. And one option is I can use MLE. Other one is MAP. MAP is useful when you have the posterior, when you have a prior on your data. So the posterior looks something like. Let me use something else. I don't know, pi. So using Bayes' rule, I can express this as the likelihood times the prior. And then there's some normalizing term, which we don't really care about because it's not a function of pi, right? So then I can write so basically I want to find the value of pi that maximizes this combination. I can take the log of this, for example. Plus a constant, which we don't care about because that comes from the normalizing term, right? And so this is equivalent. I'm basically trying to find the value of the posterior distribution that maximize the posterior distribution and find the value of the variable that I'm trying to estimate that maximizes the posterior, right? And to do that, I can break that into the likelihood contribution and the prior contribution. Yeah, and so MLE is basically the same thing, except we don't have a prior. We just maximize only the likelihood. That make sense?
I still don't see the difference between MLE and
Okay, so let's just consider a specific model, actually. So and then we'll use this as an example. Let's say I pick pi from some beta distribution. I don't know, 1, 1. Right, beta is just some distribution such that pi is between 0 and 1, right? Then let's say I pick, let's say I'm only doing generating data points xi. Which is the Bernoulli of pi, right? So you can imagine this, I'm picking the fairness of the coin according to a beta, and then I'm flipping that coin n times to get n coin flips, right? And so suppose I want to learn how fair the coin is, right? MLE is just maximizing the likelihood. So that's just the probability of x given pi. And because all the x's are independent, I can just write this as product of xi given pi, right? And then I just maximize this. Well, I take the log and usually maximize that, right? That's MLE. But in MAP, I write the posterior. The posterior is the probability of your unknown given your observations. And using Bayes' rule, I can write this as probability of x given pi, probability of pi over probability of x, right? And then I can take the log of this. So I get and so you can see I'm actually maximizing the log likelihood here. This is x given pi, which is the log likelihood, plus the prior term. Right, so that's the main difference.
You said pi it's a random distribution with parameter 1 and 1. It's really not.
Well, no, this is your prior belief, right? So the probability distribution of pi you know fully because this is what it is, right? But the probability distribution of pi given x you don't know yet because the data may give you evidence otherwise. Good question. Yep.
Someone how careful the linear algebra and the vector calculus questions?
You should be able to understand how to work with matrices and vectors. I guess in principle you could do things element-wise, but that's going to take you a lot of time. In principle you can do everything element-wise, right? But it'll take you a lot more time. It's much more efficient to know how to work with the vectors and matrices directly. You should know how to take derivatives with respect to vectors. Okay? Yep.
So there's like the MIT matrix cookbook.
Oh yeah, that's one thing I wanted to mention actually.
It's a great resource, but I mean, you can't tell us like the answer. Like how much of that should go on our.
You don't need to memorize the entire cookbook. Nowhere near.
Like matrix derivatives, things like what? I guess like what level? Like just fundamental first order.
Yeah, and second order. You should, like for example, if you want to, in the homework 1, for example, you should have been able to solve the problem where you were asked to for the gradient and the Hessian of the multi-class logistic regression likelihood. You should have been able to do that with vectors and without having to resort to element-wise operations. So I think that's a very good resource. Like you should be able to do that problem entirely with vectors and matrices, and only know the stuff from the cookbook that allows you to do that. Right, and that's a very small portion because the cookbook is a great resource. I use it all the time, but it's extremely comprehensive and has lots of stuff that you don't need to know. Yeah, I'll put a link to that as well.
I'm just curious. So by doing the MAP, is it quite similar with the regularization?
Exactly. In fact, that's how you show that these are equivalent to the regularization. You obtain the exact same objective from the regularized objective if you do MAP with these priors. Yeah.
Was that MIT material?
Say again?
Was that MIT stuff?
Oh, I'll link it after a class. It's a cookbook, basically a PDF containing lots of useful little expressions about matrix calculus, linear algebra. So yeah, I'll link it after class. You don't need to know all of it. It's a very comprehensive document. You should only understand. I mean, the first homework had the question on multi-class logistic regression. You should have been able to solve that entirely with vector and matrix calculus without having to resort to element-wise things, because that's much more tedious and you're much more likely to make an error.
Can you explain kernel approximation?
Kernel, what estimation? Oh, you don't need to know that for the exam. I don't know the details. I only prepared what I think will be tested, right? What could be tested. So I don't know the details about it enough. Offline would be better. Then I can look it up.
What was that topic?
It's called kitchen sinks. It's a method of estimating kernels. It's a fairly advanced.
Yeah, I want to ask about bound that killed in the past. You need to prepare that for exam.
I suggest you know the general overall notions of how what bounds apply. Like for example, know that the perceptron can only make a certain number of mistakes before getting a correct linearly separable solution.
Not required to prove that
I would say know the general steps of the proof. That is fair game for the exam, because we covered it a lot. We spent like 3 lectures on it. Okay.
Is the bound of the kernel perceptron the same as that of the regular perceptron?
As the regular perceptron? Yes. The proofs are identical. Yeah, because in the kernel perceptron, you have lots of like vector operations. And Jeff showed in class that in the kernel perceptron, you can think of the kernels as being points in a vector space of their own, right? And so exactly the same steps apply. Oh yeah, sorry.
So usually the kernel will produce a very complex function. But as we all know, the bias and variance, the more complex your function is, the higher, the more variance we will have. So why do we still use the kernel?
Well, sometimes, because if you don't use a kernel, you basically assuming that your data is linearly separable, right? And if your data comes from very complex phenomenon, it's almost definitely not going to be linearly separable. In most machine learning applications, it's not linearly separable.
Then what does the kernel do to reduce the variance when they have very produce a very complex?
Well, it reduces your bias, right? If your data is not linearly separable, then you're going to have a large bias if you just use a linear separator. But if you use a more complex kernel method, that'll reduce your bias. And hopefully your variance won't increase too much. In those cases where you have very complex data sets, the point where the test error is minimized, it's typically with slightly more complex decision boundaries.
So if I use kernel, I don't need to add any regularizations at all?
Yeah, I don't think, because the SVM has a very particular objective that you need to solve. You don't.
Okay, so let's say that if I use a kernel in SVM, how I draw the margin in the kernel SVM, because in the standard SVM, I can see this is like just a line, a boundary decision is a line.
Yeah.
I can draw a margin like just 2 parallel boundary like that. But in the kernelized, how can I draw the margin?
Well, I guess you just kind of think about it in the higher dimensional space. It also depends on the kernel you're given. Sometimes you have to think about it differently depending on the kernel. I'll give you an example. For simplicity, let's assume 1D, 1 dimension. Suppose I have 3 data points, plus, minus, plus. So these are not linearly separable, right? So I want to use a kernel to get a better estimate. One common kernel is just use a polynomial kernel with degree 2. And so then I'll learn in a higher dimension a function that looks something like that. Or the other way around because it's minus. But yeah, you get the idea, right? In this case, you can kind of see that for polynomial kernels of degree 2, your boundary is going to be a cross-section of some paraboloid in a higher dimension, right? So it can be like an ellipse, depending on how the hyperplane intersects the paraboloid. It can be a parabola as well. So that's one way to imagine the kernel in that case, the boundary in that case. Another way to think about it is.
No. The boundary is how I draw the margin in that case.
Oh, the margin?
Because the boundary you just draw this boundary. It's not the margin.
Yeah. Well, in this case, all these points are in the margin, right?
Yeah.
Because if you take any one of these points off, your margin is going to be very different, right? So it'll look something like this. This is your margin, right? So let's in 2D, let's say, I have lots of minuses, pluses. Then my separator will look something like this. And I can think of the margin as being, the next largest ellipsoid that touches the outside points and the inside points, right? This is not drawing. right?
For this Gaussian naive case, would be good to classify, right?
Say again?
For this case, Gaussian naive case would be good.
That's true.
But you can have the distribution from higher.
Exactly. You can put a very peaked Gaussian in the center, and then a not like a flatter Gaussian also in the center. But because the first Gaussian is very large, for this region here, the first Gaussian will always be bigger than the second Gaussian, and the second Gaussian becomes bigger once you're further out. Yeah. So Gaussian naive Bayes will work well for this data set.
So, following up on this question, so let's say I can fit a line with a degree of 10, a polynomial line with a degree of 10. Instead, can I think of the kernel as something that will let me do this without going to the degree of 10?
Without specifying?
Like, if my data is separable only by drawing a line that is, to a degree of 10,
Yeah.
can I make it less dimensional by using a kernel?
Not necessarily, because for the polynomial kernel, you have to specify the degree as well. So the polynomial kernel is just,
So not polynomial kernel, but the regression line that we talked about earlier to regularize with the bias and variance, right?
Okay.
As the complexity increases, your variance increases.
yes.
So can I get around going to that level of complexity by putting a kernel and?
Well, one thing you have to keep in mind is that what you're trying to minimize is your test error. And the only way to get your test error is to test it on additional data, aside from your training data. So to do that, you want to use some sort of cross-validation technique or hold out some part of your data set and then train it on the other part, and then compute the test error on the held out portion. So you won't be able to, I guess.
So what I'm asking is the points that were separable only by a very complex line.
Yeah.
Can I think of those points as separable, linearly in a higher dimension? Therefore, I can apply a kernel in the higher space.
Yeah. Yes, that you can do. Yeah. So I'll just repeat. For very complex distributions of points, where it's not very clear in the example space where that they're clearly linearly separable, you can project them to a higher dimensional space using some sort of feature map, and hopefully in that space it'll be linearly separable. And
so basically, if there were no kernels at all, the only way I could have done that is by fitting a 100th degree polynomial or things like that.
well, that does correspond to a kernel. And any feature map which projects to a higher map, I can take phi of x inner product with phi of y for any 2 points x and examples x and y,
Okay.
and that gives me a kernel automatically. So that's actually one way to construct kernels, which is very useful.
What is the kernel that you're using here?
Say again?
What is the kernel?
Oh, I was just mentioning the polynomial kernel.
So I'm asking that how did you choose the kernel for the data set?
Well, that's kind of something that you have to choose yourself. That's part of the process.
What if here you use a polynomial kernel? What's the boundary?
Well, it'll be. So it'll depend on the dimension d, right? If dimension d is 1, it'll be linear, right? This is just linear, right? But if it's 2, then it'll be any. You should think of any two-dimensional function, two-dimensional polynomial in higher dimensional space. So that's like a paraboloid, for example. And then you can think of cross sections to that paraboloid. So in that case, your boundaries will be some sort of ellipsoid or a parabola. And you can think of higher dimensions that way. It's a bit more difficult because high dimensional polynomials in multi-dimensional space is kind of hard to intuition. Right?
It's very hard to realize the boundary by giving a kernel. So what if you add another polynomial kernel to this kernel? So now you have a polynomial kernel. What if you add another term?
Another term? What kind of term?
Like a linear term, like
like that. Well, this one will automatically capture first order behavior by itself.
For such kind of kernel, how could you realize the boundary based on a given example?
Like, I'm having difficulty understanding your question. Could you say it again one more time?
Yeah, so by giving a kernel, how could you realize the boundary, the decision boundary, based on the sample?
Just so suppose you're given a kernel and you're given a data set?
Yes.
Well, we're not going to ask you to be able to do that for arbitrary kernels or and arbitrary data sets, right? The only way to do that correctly is to actually run it through a computer and simulate and run the algorithm.
How could you realize the boundary and the support vectors? Because in our homework appears.
Yeah. Yeah. So I would say there are two methods. One is useful for say radial basis functions, for example. I can't go into too much detail because it's there's still the grace period for the homework isn't until Sunday, I believe. But yeah, so let's go back to this case. So one way, like suppose you have a radial basis function kernel, like a Gaussian, is just to think of them as blobs, as Ada elegantly put it. And these are summed together. So your function would look something like this. Right? And then from that way you can think of the decision boundary as like a sum of kernels placed at each data point and weighted by their class sign, right? And then that resulting function, you want to see where the level set is, and that'll give you the decision boundary, right? Another way to do it is I guess simpler with if you use a polynomial kernel of degree 2, then you consider what the boundary looks like in the higher dimensional space, right? So like you project this up somewhere. And then that looks something like this, right? Yeah, so different methods, to think about it, I guess, yeah.
Is there any practice exams or previous exams available online?
I'm not sure. I have to look for them.
But TA doesn't provide any practice exams?
Not yet. We're still discussing that. Yeah.
If Gaussian naive Bayes, but always linear transfer.
No. Oh, naive Bayes. No.
No always.
No.
Why?
So a nice way to think about Gaussian naive Bayes is that it's the same thing as Gaussian Bayes, the full version, but your covariance matrix for each Gaussian is diagonal because you assume that every dimension is independent of each other, right? So your normals, you assume your covariance matrix K is diagonal. So what that means when you draw it, like in here, I can, for example, have one Gaussian that is very peaked, right? Actually, let's do it in one dimension. That's easier to see. So in this case, the values on the diagonal are very high, right? Or is that high? No, they're very low. they're very, very small. Because it describes variance, right? And if the covariance values are very small, that means that the values don't vary as much, right? That's pretty intuitive. Whereas my second Gaussian, I can have something like this, which is exactly the same center, but the values of the diagonal in the covariance matrix are very large, so it's very spread out. And so your separator are these 2 points, right? So in 2 dimensions, you can think of this as being, you can have like ellipses, right? You can have circles. Yeah. And you can actually get much more interesting shapes if you don't assume that it's naive Bayes, in which case K is a full covariance matrix. In that case, you can get any kinds of conic sections. And you can derive that fairly easily. I think we showed it, that it's any kind of quadratic form is the naive Bayes. I think RT posted on Piazza. Yep.
Why is it that in the ridge regression parameters that if the beta is the Laplacian, then with 0 mean, and why its Bayes solution is small?
So ridge regression refers to L2 regularization. And that is related to a Gaussian prior on the parameters. L1 regularization, also known as lasso, is connected to the Laplace distribution on the priors, on the parameters, right? Yeah, let's. So just to draw the Laplace distribution again. It looks something like that. There's like a kink. There's a non-differentiable point at 0. So suppose you wanted to optimize a likelihood, a log likelihood, let's say. I don't know, like this. Some likelihood, some objective, right? It's probably not that way. And I'm doing MAP, maximum a posteriori. So I'm combining the likelihood term and the prior term, right? And I wanted to optimize this. One way to optimize it is to find the gradient and set it equal to 0. That'll give me the optimum, right? But since I have a non-differentiable point, that means I have to explicitly consider this point separately. So like I'm explicitly testing to see if the maximum occurs at the 0 point. And because it like rises so sharply at 0, things that are close enough, to 0 will want to be equal to 0 itself. Does that make more sense? Yeah.
It might be easier to understand from like the brute force optimization method. Like if you write the objective function that we're minimizing or maximizing on the board, like with the penalty term, right? When we're solving a regression problem, we want to minimize our error on the training data, right? So that's part 1 of the objective function. And when we add a ridge or lasso penalty, we add this other term into the objective function. And so if I want to minimize f, then for every x that's non-zero, I'm going to take a hit, right? So if I'm trying to find the minimum of this function, it's in my interest to set as many of those xi's to 0 as I can without sacrificing f. Does that make sense?
Thanks. Go ahead. Say again?
Can you repeat what you said? I couldn't hear that.
Oh yeah. She said that if you look at the optimization itself, you're trying to minimize this function, right? But every time xi is not 0, then you're basically paying a price. So this tends to make xi 0 because in that case, that term will have 0 cost for this prior term. Make sense? Yeah.
So this is more of a logistics question. I feel like with all the other subjects, we had homework to drop by on online questions, and we'll have online questions for this stuff, but we haven't had homework on this yet. You recommend any like resources online to find like practice question? Because they also don't go over too many examples in class, so I'm struggling to like think of questions that they could ask on future direction.
Yeah, sure.
The online questions. Yeah, but not homework. So there's no in-depth questions. There's just surface level questions on stuff. And I assume that the tests can be somewhat between homework level and surface level.
Yeah, I think that's accurate.
But so like, I mean, it's not something I.
So I think we were going to link to previous exams from prior semesters of this class. I don't know who's supposed to do that, but you can also find them with like a quick Google search.
Yeah.
And those are totally fair game. Those are very similar to the kind of things we would ask.
Yeah.
Using recitation, we get a lot of details in SPM. Like we didn't go through as much in the class, right? So I was supposed to go through the recitation notes for SPM.
I think that you should know how to find an SPM exam, how to do stuff with an SPM. The intuitive understanding is obviously the most important thing, but you may be asked something detailed about SPMs.
Yeah, I think you should know the optimization itself involved.
Is it a closed book exam?
Say again?
Is it a closed book exam?
Yes, except for one sheet page, front and back. No electronic equipment.
One sheet page, one side or two side?
Two side.
Sorry, another question. So in class you said that, I think you did last, the new method.
Yeah.
Said that wouldn't be on the exam.
That's right.
And that's the only way we've learned so far to really optimize the SPMs. So we wouldn't, by like induction, we need like not ask us what the actual form.
Well, yeah, what he introduced are like numerical methods, like things that I would code in a computer.
Okay.
We may ask you like it'd be fair to ask you for like, because we asked you in the homework, like to provide like the gradient or the Hessian for an objective and feed that to a hypothetical optimization algorithm. And if we do ask you specifically about those optimizations, we would give you the steps required, right? So, yeah.
Can there be any proofs in the exam that this wasn't covered?
Yeah, I would say it's fair. Obviously, there are time constraints, so we're not going to ask you for like incredible details, but I would say it's fair to know the overall gist of some of the proofs.
More like asking if there would be like a simple proof that would be simple, but it's never been, we never seen it, for example.
Yeah. I would say it's
very hard and really takes very little time.
I would say the homework questions and the online questions are a much better representation of what you'll see in the exam. Okay? Yeah.
In 2D dimension, the contour of Gaussian distribution will be an ellipse, right?
That's correct.
And what if two variables are independent from each other? Then what will be the contour look like?
What was this last part of your question? So let me just repeat. The multidimensional Gaussian is going to have the level sets are going to be ellipsoids. That's correct. Then?
When the two variables are independent from each other, then what will the contour?
So you're trying to think of the of Gaussian Bayes classification, for example, the not naive Bayes. Yeah, those. If you look at the notes, Artie showed that the decision boundary can be any degree 2 curve. So in this case, it would be any conic section. You can have ellipsoids as a decision boundary. You can have hyperbolas. You can have lines. Yeah.
So now you use the forcing kernel for the classification, the question you just asked.
Oh no, this is not a kernel method. This is Gaussian Bayes. Yeah. So you're approximating that you're basically hypothesizing that your data was generated from drawing from Gaussians to Gaussians, right? Yes?
If we have a nonlinear decision boundary, is there a geometric meaning to W? Because it used to be the normal for the
Yes.
decision boundary. And
Yeah.
It seems like it just isn't anything.
It's the normal of the linear decision boundary in the higher dimensional feature space. Yeah, that's the geometric notation.
Can you talk about the Gaussian kernel? What will its shape like? And what's its parameter will impact its shape?
The Gaussian kernel, so suppose like you're saying a radial basis function as a kernel for kernel methods like kernelized perceptron or SVM. Is that the question? Yeah. There are different conventions, but generally it's like I think it's so here you just have a single width parameter that basically just tells you how wide the kernel is. But otherwise it looks very much like a Gaussian. Yeah, so let's make this x minus y. It looks something like this. Right. If sigma is very, very large, then something like that. Oh yeah, sorry. Say again?
So the data set is two-dimensional. The samples are two-dimensional. So you use a Gaussian kernel to run the boundary of the two classes of samples.
Yep.
What's the shape of the boundary?
Well, from this you can see.
Circle can sometimes can have two branches. How do you realize?
Well, you can see here that sigma has to be constant for all of the kernels in your example space, and you notice that this is isotropic. It's symmetric entirely, so it has to be spherical.
Also, that is in problem 1 on homework 2.
Oh, I'm sorry.
So,
I'll stop
like
talking
what
then.
the boundary would look like is kind of on homework, so
Okay.
7:15.
Oh, okay. So yeah, we're out of time. Let's see. How about we take the questions after? Is that better? Yeah, let's take the questions offline. Is that all right? Because